Hello, I Anand Jain from Hanumangarh, Rajasthan welcomes you to your favorite Shridevi Classes YouTube channel where we inculcate interest and confidence in science and engineering subjects. Today in our class 12th physics playlist, we'll study applications of Kirchhoff's law in our chapter electric circuit, and we will study how a circuit is solved by assumption of branch currents and then writing Kirchhoff's voltage law equation in independent loops. And then we will also learn how two linear equations of two variables are solved by matrix method using Cramer's rule. So let's start application of Kirchhoff's law, KVL and KCL, and in next 15 minutes we will learn everything for preparation of this examination question. Here in this circuit we have given 3 resistances and 2 voltage sources connected in a particular manner. Now in this circuit there is no common current flow path, or there won't be identical current in resistances. So none of the resistance is in series to any other resistance. Similarly, this 12 volt magnitude and this 6 volt magnitude is different. So voltage of 3 ohm and 4 ohm is not the same. Similarly, the voltage of 5 ohm is different from voltage of 3 ohm and 4 ohm. So none of these 3 resistance is parallel to each other. So we can't apply series parallel simplification to get information of current in different branches. But by the use of Kirchhoff's two law, Kirchhoff current law KCL and Kirchhoff voltage law, we can easily analyze this interconnection of resistances with batteries. First we understood the basic statement of two Kirchhoff's law, Kirchhoff voltage law and Kirchhoff current law. Kirchhoff current law is applicable to a node junction point where more than two branches meets together. The basic statement of Kirchhoff current law says that at any junction of electric circuit, summation of all incoming current is equal to summation of all outgoing current. In blue frame and yellow highlight 3 current I1, I2 and I6 are incoming current to this junction. So summation of all incoming current is equal to the other 3 currents I3, I4, I5 are outgoing currents at the junction. So summation of outgoing current is equal to summation of incoming current. Now this relation can be used to find out one unknown current if other incoming and outgoing currents are known to us. The other Kirchhoff law is Kirchhoff voltage law, KVL, and KVL is applicable to a closed part of circuit known as loop or mesh as shown in this yellow highlight or in this blue frame. To write Kirchhoff voltage law equation in a loop, we have to travel in loop. We can start from any node point A, B, N or E or any other convenient point joining resistance arm and voltage source. But we prefer left bottom node of loop as A here, and we have to travel either in clockwise direction or anti-clockwise direction in loop, and we will prefer clockwise rotation, and we will cross EMF source, resistances and check voltage rise and drop, and will frame two accounts, one of voltage rise, another one of voltage drop, and summation of all voltage rise is equated to summation of all voltage drops. And this would become the statement of Kirchhoff voltage law, which says that in a loop the summation of voltage rise is equal to summation of voltage drops. So let's first understand how rise and drop are considered and how their magnitude is obtained in a voltage source and in a resistance branch. For a voltage source, the positive longer arm is high potential end, and if we travel and cross voltage source from high potential to low potential way, then a voltage drop will take place, or a vice versa movement from low potential to high potential may result in voltage rise, and the rise or drop of voltage is always equal to magnitude of EMF of voltage source irrespective of current flowing through the voltage source. So in rise drop calculation of voltage for a voltage source, current has no concern, whereas in resistance the direction of current will decide whether our movement will have voltage drop or a voltage rise, as current always flows from high to low. So when we travel along the direction of current from high potential to low potential across a resistance, then a voltage drop will take place, and a vice versa movement against current direction will be a movement from low potential to high potential. So a voltage rise will take place, and as per Ohm's law, V is equal to IR says that the magnitude of voltage is directly proportional to current flowing through the resistor, and if there is no current in resistor, there won't be any voltage drop across that resistor. So the direction decide rise and drop, and magnitude decide the amount of voltage drop across resistor. In this given circuit, 3 resistances 3 ohm, 4 ohm and 5 ohm values are connected to 2 voltage source, one of 12 volt and another one of 6 volt as shown in this figure, and we have to find out current in all resistance branches. Now in this circuit circuit, there is neither a common single current flow path of same current, nor there is a common potential among any two resistances. So these three resistances are neither in series nor in parallel. So we cannot apply series parallel simplification procedure to analyze this type of question. So this circuit is given to us and we have to find out current in these 3 ohm, 4 ohm and 5 ohm resistances, and we'll use branch current method. Let's first understand what is branch. The elements which link together at a point position, then that point position is known as node. So in this circuit there exist two nodes, one at top side and second at bottom side, and between these nodes the elemental connection is known as branch. So there exist 3 branches. Now in branch current method, the first step is assume currents in branches. So we could assume currents of 3 branches by 3 unknown, but what we'll do, we'll use Kirchhoff current law at node, and that will reduce number of unknown in our assumption. Let's assume current in 3 ohm is X, current in 4 ohm is Y, and when we apply Kirchhoff current law at this node, then incoming current X and Y when summed up give me outgoing current X plus Y. So that X plus Y will become current of 5 ohm. So we have assumed current of all 3 branches, but we have only 2 unknown. One unknown is reduced by the use of Kirchhoff current law at this node position. Now for determination of value of unknown current, we have to write 2 equations, and those 2 equations comes from Kirchhoff voltage law, and Kirchhoff voltage law will be applied in 2 independent loop. One is this shown in blue frame, and other independent loop is shown in this magenta frame. And in these 2 loops, when we write Kirchhoff voltage law equation and solve those equations, we will get assumed current of these branches. Let's write Kirchhoff voltage law equations. To write Kirchhoff voltage law equation in a loop, say A, B, N, E, A, we have to travel in this complete loop and consider summation of voltage rise is equal to summation of voltage drop. We can start our travel journey from any node, and as a standard practice we will prefer left bottom node position of loop for our travel. We can travel in loop either in anti-clockwise direction or clockwise direction, and we will prefer clockwise direction as a standard practice. And when we cross this first 12 volt source, we are moving from low potential to high potential position. So irrespective of current flowing in this voltage source, so 12 is placed in rise side. Now we are crossing 3 ohm resistance, and our movement is along the direction of assumed X current in this resistance, and current is flowing from high potential to low potential. So our movement from high to low means it's a drop, and drop of IR 3X is placed in drop side. Now when we cross 4 ohm resistance, we are moving against its assumed Y current. Current Y is moving from high potential to low potential, and our movement is low to high. So it's a rise. So 4Y will be taken as rise. And finally, when we cross 6 volt source, we are moving from high potential to low potential. So it's a drop of 6 volts. It is quite interesting that here there exists 2 EMF source calculation. One 12 volt comes in right side as we have moved from low potential to high potential, and the other 6 volt was placed in drop side as during our movement we have moved from high potential to low potential. Similarly, one IR drop in resistance 3X was in drop as we have moved in the direction of current, and another IR drop of 4 ohm 4Y was in right side as we have moved that resistance against current direction. For matrix method of simplification, we will rearrange this equation. First, the coefficient of X 3 is written, then 4Y with side change become minus 4Y, and to other side the number figure 12 and 6 when transferred to other side become minus 6 results in 6. So this become our first equation. Similarly, in other loop E, N, C, D, E, we once again start our travel journey from left bottom node E. We will again travel in clockwise direction, and first when we cross 6 volt source, we are moving from low potential to high potential. So this 6 volt is in right side. Now in 4 ohm resistance, we are moving in the direction of current from high potential to low potential. So this 4Y comes in drop side, and finally across 5 ohm again we are moving in the direction of current. Current moves from high to low. Our movement is also high to low potential. So it's a drop, and it is IR 5X plus Y. Again, for matrix method of simplification, the coefficient of x is 5 and coefficient of y 5 and 4 becomes 9, and to other side the number figure is 6. So 5x plus 9y equal to 6 becomes our second equation. Now these two equations, 3x minus 4y is equal to 6 and 5x plus 9y is equal to 6. When solved by matrix method, we have to rearrange these equations in matrix, and the coefficient of x 3 and 5 are placed in first column, coefficient of y minus 4 and 9 are placed in second column, and with this 2 by 2 resistance matrix, another matrix of unknown current x and y is taken, and the product of these two matrix is equal to coefficient matrix 6 and 6 in these two equations. As we know, in matrix multiplication, the column element of first matrix are multiplied to row elements of second matrix. So 3x minus 4y equal to 6 becomes our first equation, and similarly 5x 9y equal to 6 become our second equation. So these two equations are written again in matrix form as shown here, and it is quite easy. The coefficient of x are written in first column, coefficient of y are written in second column, and then we have assumed current matrix, and then we have equal to elemental matrix. Only the matrix notation, this big bracket at appropriate position should be placed. Once the two equation 3x minus 4y equal to 6 and 5x plus 9y equal to 6 are written in matrix form, we can find out unknown assumed branch current x and y using Cramer's rule. And to apply Cramer's rule, the unknown x can be obtained as a ratio of two determinate values of two matrices. Now the bottom matrix is same as this resistance matrix 3 5 minus 4 9, 3 5 minus 4 9, and at numerator side the first column of matrix, which is coefficient of x, should be replaced by coefficient of equal to matrix column, that is 6 6. So this matrix become 6 6 minus 4 9. Now to get determinate value of any matrix, we have to make cross multiplication, and for diagonal element 6 and 9 the product is taken, and for off diagonal cross product the product should be sign changed. So the product is minus 4 into 6, and when sign changed it become plus 24. So at numerator 6 9s are 54 and 4 6s are 24 are summed up. Similarly at denominator side, when product of diagonal element is done, it is 3 9s are 27, and for off diagonal with sign change it is minus 4 multiplied by 5 minus 20 with sign change it become plus 20, and resultant x current will become 78 by 47 ampere. Similarly, as per Cramer's rule, the second unknown y can be obtained as a ratio of two determinate value of two matrices. Now the denominator matrix is same resistance matrix 3 5 minus 4 9, 3 5 minus 4 9, but at numerator side the coefficient of y minus 4 and 9 will be substituted by equal to column matrix 6 6. So our new matrix would be 3 5 6 6. Now we can find out the determinate value of two matrix as earlier. The product of diagonal element is taken without sign change as 3 6 is 18, and the product of off diagonal element will be sign changed and it become minus 30, and the denominator matrix is same, so its determinate value is again the same 47. So this calculation is already done, and simplification will fetch the value of y equal to minus 12 by 47. Now this negative answer is not a wrong answer. It just says that the assumed y current got a magnitude 12 by 47, but in reality its direction is opposite to our assumption, whereas the positive answer of x indicates that current in 3 ohm is in the same direction as assumed direction, and its magnitude is 78 by 47. And now the current of 5 ohm is x plus y, and we can substitute value of x and y, and the negative value of y when added will be ultimately subtracted from 78, and 78 and minus 12 results 66 by 47 as current of 5 ohm. So current of 3 ohm is x, 78 by 47 in assumed direction. The current of 4 ohm is 12 by 47, but its direction is opposite to our assumed direction, and current of 5 ohm is 66 by 47 in assumed direction. For conceptual clarity of Kirchhoff's law application, let's exercise one more problem. We have given 3 resistance, 3 ohm, 4 ohm and 1 ohm and 2 voltage source 12 volt with positive end to upside and 6 volt with reverse direction of high polarity end as shown in this diagram, and we have to find out current in 3 ohm, 4 ohm and 1 ohm. So as discussed earlier in branch current method, we'll assume current in 3 ohm as X. Now the current of 4 ohm with this polarity of voltage is considered Y as shown in this diagram, and when X is incoming current, Y is outgoing current, so the remaining outgoing current as per Kirchhoff's voltage law will become X minus Y. So again, using Kirchhoff current law at this junction, we have reduced number of unknown to only 2 and assumed current of all 3 branches as X, Y and X minus Y. Now to determine the unknown X and Y, we have to write 2 equations in 2 independent loop. One is this yellow highlighted loop and the second one is blue framed loop, which also have a new 1 ohm branch. To write Kirchhoff voltage law equation in this yellow highlighted loop, we will start our travel in the loop from left bottom node A and once again travel in clockwise direction. So when we cross 12 volt source, it is low to high 12 volt rise. So in rise column we will place 12. Now across 3 ohm we are moving in the direction of current from high to low, so it is 3x drop. So in drop side we have 3x. Now in 4 ohm we are again moving in assumed Y current, so 4y is again a drop. And finally, across 6 volt source, our movement is from low to high, so it's 6 volt rise. So both voltages are in rise side and both resistance voltages are in drop side. For matrix method of manipulation, we will rewrite this as coefficient of X as 3, coefficient of Y as 4 and equal to side got a number 18. This become our first equation. Similarly, in second loop, again we start our travel from left bottom node F and travel in clockwise direction. So in our travel F, C, D, E, A, F, when we cross 6 volt, it is high to low 6 volt drop. So in drop side, we will place 6. Now in 4 ohm, we are moving against current. So it's a 4y rise. And in 1 ohm, we are moving in the direction of X minus Y current. So it's a drop of 1X minus Y. So total drop become equal to total rise. And our journey is completed when we come back to the starting node position once again. Now this equation is rewrite for matrix manipulation as 1x. This 4y when side change become minus 5y, and this number 6 when transferred to other side will become minus 6. So our second equation is x minus 5y is equal to minus 6. These two equations can be written in matrix format with one matrix with coefficient of x 3 and 1 as one column and coefficient of y 4 and minus 5 as second column. Now the unknown assumed branch currents are there in second matrix. This big bracket indicates start of matrix and this end bracket indicate end of matrix, and equal to side got a column matrix 18 and minus 6, and matrix multiplication of column elements with row elements indicates 3x plus 4y equal to 18 as first equation and 1x minus 5y is equal to minus 6 as second equation. Now unknown assumed branch current x and y can be obtained by Cramer's rule, and you will find this matrix method very systematic and error free. The unknown x is ratio of determinate value of two matrices, and one matrix is the same 3 1 4 minus 5 in denominator side, and to numerator side we have to replace the coefficient of x. In first equation it is 3x and in second equation it is 1x. So this 3 and 1 coefficient of x are replaced by column of equal side matrix 18 and minus 6. So this new matrix will become 18 minus 6 4 and minus 5, and the ratio of determinate value of these two matrices will give me the value of x. For determinate value, the diagonal element are multiplied without sign change. 18 when multiplied with minus 5 fetch me minus 90, and off diagonal elements are multiplied with sign change. So minus 6 multiplied by 4 become minus 24, with sign change it become plus 24. Similarly in denominator matrix 3 and minus 5 diagonal elements are multiplied without sign change, and off diagonal elements are multiplied with sign change. So it becomes minus 15 and minus 4 minus 19, and numerator calculation becomes minus 66. So minus sign when cancel out, my x current will become 66 by 19, and positive answer indicates that assumed current and real current are in the same direction, and this current of 3 ohm is 66 by 19 ampere. Similarly, from this matrix format of equations, we can find out unknown y. And to find out y, we have to use once again Cramer's rule. As per Cramer's rule, the y unknown current is ratio of determinate value of two matrices, and the one matrix is same this coefficient matrix 3, 1, 4, minus 5, which was earlier in denominator of x, and ultimately when it is solved, it becomes minus 19. Now at numerator side, this time the coefficient of y 4 and minus 5 must be replaced by coefficient of column 2 equal to side, and it is 18 minus 6. So this numerator matrix is 3, 1, 3, 1 and 18 and minus 6. For its determinate value, the diagonal elements are multiplied without sign change, and off diagonal elements once multiplied and sign is changed. So it becomes minus 18 and minus 18, minus 36, and when this negative of numerator and denominator are cancelled out, it becomes 36 by 19, and positive answer indicate that assumed current and real current are in the same direction, and current of 4 ohm is 36 by 19. Now we can also find out current of 1 ohm as x minus y, and x and y when subtracted, the resultant current of 1 ohm will become 30 by 19 ampere, and positive answer indicates that assumed current and actual current are in the same direction. So we have understood applications of Kirchhoff's law by two examples, and we have also understood how matrix method is used with Cramer's rule to find out unknown currents. A practice of one or two problem by your own effort will definitely ensure your exam success. Our other learning videos of this playlist are equally good, and you can use them in your studies and also share them with your friends. If you want advantage of our online doubt clearing classes and needs dedicated study notes, do join our YouTube memberships by pressing join button just beneath. Happy learning and have nice time. Thank you very much.